did in this last one is we found our probability by taking how many possibilities there were and dividing by the total number of possibilities. We were talking about how many girls there were, which was that we're talking about there's only one option for girls, or out of how many options when you have a baby? 2, boys or girls. That's kind of the idea when you're finding probability, is whatever you're looking for out of the total. Now, the idea is, that's always going to be the idea behind these. Classical probability or theoretical probability is what should happen in theory. Well, when we had our girls and boys example, we were looking at the probability of having a girl, which is that there's only one way to get a girl. There's only 1 out of 2 options that were girls out of the total of 2 options, which gave us a probability of 0.5. So in theory, you have a 0.5 or 50% chance of having a girl. However, you might do an experiment and find out that somebody actually has, if you actually do an experiment, has 10 kids, let's say, and let's say 6 of them are girls. Your chances of actually selecting a girl there is a little bit different. You had 6 of them that were girls out of a total of 10, which is 0.6. That is the difference between classical theoretical probability and what's called empirical probability. Empirical, which is what we just found, the 0.6, is what actually did happen as the result of an experiment. Whereas in theory, the value of the probability of having a girl should be closer to 0.5. So the theoretical probability is what should happen in theory, whereas empirical probability is what actually did happen as a result of a probability experiment. They're still found the same way. It's part over the whole and then turned into a decimal. It's just whether or not it's based on what should happen in theory or what actually did happen as the result of a experiment. That's the difference between classical and empirical. Now, the thought, though, is, as we continue into the law of large numbers, is if you happen to continue doing this experiment over and over and over and over again, is that you'd eventually get up to, let's say, really large numbers. We'd get up to our experiment having, let's say, a total of 1,000 kids, and you'd have 500 and let's say 20 that were girls. So as you do this more and more, you'd get 520 out of 1,000, which would be much closer. You'd get 0.52, which is much closer to the 0.5 to the 1/2 than the 0.6 we got. So the idea is the more and more you do this experiment, so we'd be looking at, instead of 1,000 kids, 10,000 kids, we'd get closer and closer to the 0.5 that we think we should be getting. It wouldn't be exactly 0.5, it might be a little bit bigger or a little bit smaller, but it would get closer and closer the more, the larger our total, the larger our sample space that we'd be looking at. So that's why when people do experiments, they say, oh man, we need a lot of data in order to show something, because you don't narrow in on real values unless you do an experiment enough times. So that was why in one of the first chapters we said you really cannot have small samples. Let's take a look at a couple more examples of finding probabilities. When playing roulette at the Mirage Casino, you have chances of 18 out of 38 of winning if you bet that the outcome is an odd number. Express this likelihood as a probability. So just like before, we're going to take the part, which is that there are 18 odds out of a total of 38 values, and we're going to figure out what that is, again, as a decimal. because that will be our probability. So you'll go to your calculator and you'll type in your 18 divided by your 38, and you'll round a little bit here. You'll get 0.47, and that's our probability. You're done. You don't actually need to worry about reducing the fraction unless they ask you to. They just want us to turn it into a decimal here. Next one, on a multiple choice test with 5 possible, one more, I skipped one here. When randomly selecting a day of the week, you're certain to select a day containing the letter Y. Well, let's see. There are a total of how many days in the week? 7. How many of those 7 days of the week end in the letter Y? Well, all 7 do, which means if we divide 7 divided by 7, we get 1. Remember, 1 is the same thing as saying that the chances of selecting something containing the letter Y is going to be 100%. It means it's definitely going to happen. That's why they actually even said you are certain. They're giving you a hint that you will get the answer 1. It's going to happen. You will definitely get something that contains the letter Y if you're selecting a day of the week. So you just type in the number 1 and you would be done. That is your probability. Let's look at the next example. On a multiple choice test with 5 possible answers for each question, what is the probability of answering a question correctly if you make a random guess? So we're on a multiple choice test, and they say that there's 5 possible answers to choose from. So that's first of all what we're looking at, is that's our total, is we've got 5 possible answers. Now, on a multiple choice question, how many of them are actually, we want to get the question correct? Well, there's only 1 correct answer on a multiple choice question. So we take the 1 divided by 5 and we'll get 0.20. That's our probability. It means that there's a 20% chance of us getting it correct if we're just randomly guessing, because only 1 out of the 5 answers is actually correct. Let's take a look at the last example here. When Mendel conducted his famous genetic experiments with peas, one sample consisted of 428 green peas and 152 yellow peas. Estimate the probability of getting an offspring that is a green pea. So we want to look at specifically only getting a green pea. Well, how many of them are green? 428. So we're going to be starting out with our 428. The question is, out of what? Well, I need a total number of peas. Well, to find out the total number of peas, well, I don't have that anywhere in my problem. It means I'd need to take my green peas and my yellow peas and add them up to figure out what my total is. So first of all, I'd have to take the 428 and the 152 and add those up to get a total of 580. So that I know, again, how to take the green peas, which is the 428, divided by the total number of peas, which was the 580 we just found, and that would give us a decimal of 0.74, and that's our probability. So be careful. They don't always give us the total. You may have to actually find it.